Jai Hind to all. In this particular lecture of the subject Electrical Machines 2, KEE 503 as per AKGEC syllabus, I am going to discuss certain numerical questions based upon three-phase induction motor. Starting with question number 1, let us first try to understand the question. An 8 HP 3-phase 4-pole squirrel cage induction motor is connected to 400 volt 50 Hz supply. So, what is given in the question is that we have got an 8 HP motor, 3-phase, number of poles given the question are 4 for this particular motor. This motor is connected to 400 volt. It is connected to 400 volt 50 Hz AC 3-phase supply system. The motor is operating at full load with 5% slip. So, operating slip of the motor is given as 5%. This is full load operating slip of the motor. We need to calculate the following. The speed of revolving field relative to the stator structure. So, we need to calculate the speed of rotating magnetic field, that is NS, relative to the stator structure in first part of the question. In second part, we need to calculate the frequency of rotor currents, the speed of rotor MMF relative to rotor structure in third part, the speed of rotor MMF relative to stator structure in the fourth part, the speed of rotor MMF relative to stator field distribution in the fifth part, and in the sixth part, the question is asking, are these conditions right for the development of the net unidirectional torque, right? So, let us find out the answer for all these parts. Starting with the first part of the question. The question is asking for, it is the first part, the speed of revolving field relative to the stator structure. The speed of revolving field or rotating magnetic field relative to stator structure is given as Ns equals to 120 F by P. Here, F is the supply frequency. It is supply frequency. P is the number of poles for which the machine is wound, right? So, in our case, the frequency of supply is given as 50 Hz and the number of poles for which the machine is wound is given as 4. So, as per this, we can very well determine the first part of the question as Ns equals to 120 multiplied by 50 divided by the number of poles 4. Solving this, you will get the answer as 1500 RPM. This speed is actually in RPM, where RPM is the revolutions per minute. So, we find here that the rotating magnetic field is making 1500 revolutions per minute. The answer key of the question is given over here, and the answer for the first part of the question is 1500 RPM. Right. Now, let us move to the second part of the question. The second part of the question says that we have to determine the frequency of the rotor currents. So, as you may be aware that the frequency of EMF or current in rotor circuit is given as F2 equals to SF, where F is the supply frequency, F is the supply frequency, S being the operating slip of the machine, operating slip of the machine. So, knowing F and knowing the operating slip, the frequency of rotor induced current F2 can very well be determined as S times F. So, F2 can be written as S times F. Now, let us recall that in the question, the operating slip of the machine is given as 5%. This is the full load operating slip of the machine. So, with a slip of 5%, the S times F 0.05 multiplied by F being the supply frequency of 50 Hz. So, this much Hertz is the frequency of induced currents in the rotor circuit. So solving this, you will get the answer as 2.5 Hertz. The answer is given in the question. It is 2.5 Hertz, right? Now let us move to the third part of the question. In the third part, the question is asking the speed of the rotor MMF relative to the rotor structure, right? The speed of rotor MMF relative to the rotor structure. So let us now try to find it out. In third part of the question, speed of rotor MMF relative the speed of rotor MMF relative to rotor structure. So, speed of rotor MMF relative to the rotor structure. The speed is given as 120 F2 by P, right? So solving this, 120 F2 is S times F. So we can also write it as SF divided by the number of poles developed in the rotor. Number of poles developed in the rotor are same as the number of poles for which stator of the machine is wound. So solving this, we can substituting the values. 120, the operating slip is 0.05 multiplied by the frequency of 50 Hertz divided by the number of poles 4. Solving this, you will get the speed to be equal to 75 RPM, right? So it is given in the question. Now let us move to the fourth part of the question. The fourth part is asking for the speed of rotor MMF relative to stator structure. Let me move to the next slide. We need to determine the speed of the rotor MMF relative to the stator field. The speed of rotor MMF relative to stator field, right? And the fourth part was this part. The speed of rotor MMF relative to stator structure. In fact, let me correct the fourth part of the question. Fourth part is asking for the speed of rotor, not of rotor MMF. So in fourth part, we need to determine the speed of rotor relative to the stator structure. Speed of rotor relative to stator structure, right? So the speed of rotor relative to stator structure is rotor speed NR, and NR can very well be determined as NS into 1 minus S. NS is the synchronous speed, S is the operating slip of the machine. So here, solving this, we'll get the speed. If we are putting NS in RPM, so we are going to get the NR, which is the rotor speed in revolutions per minute. So substituting the values, I first need to determine the synchronous speed of the machine NS. So we know that NS equals to 120 F upon P. This gives us NS to be equal to 1500 RPM. The same thing we have established earlier as well as first part of the question. So NR would be equal to 1500 1 minus 0.05. And solving this, you will get the rotor operating speed as 1425 RPM. So this completes the fourth part of the question. Now let us move to the fifth part of the question. The fifth part is asking for the speed of rotor MMF relative to the stator field distribution. And before that, we will also determine the speed of, let me write down here. We are here determining the speed of rotor MMF relative to the stator first, right? So speed of rotor MMF relative to stator structure. Relative to stator structure, the rotor MMF field would be equal to the summation of two fields, would be summation of two speeds. One is the operating speed of rotor itself and second is the rotor MMF speed with respect to rotor structure. So here I'll write rotor speed plus rotor MMF speed with respect to rotor structure. So rotor is rotating with respect to stationary stator and the rotor is rotating at a speed of 1425 rpm. We know that, right? Besides this, we also know that the rotor MMF is rotating at a speed of 75 rpm with respect to rotor structure itself, right? So the summation of these two will give us the speed of rotor MMF with respect to stationary stator structure. So I can write here that rotor speed, that is 1425 rpm, plus rotor MMF speed with respect to rotor structure, this was equal to 75 rpm. So the summation of these two comes out to be 1500 rpm, right? So this is 1500 rpm. Now let us consider what the question is asking next. It is asking for the rotor MMF relative to stator field distribution. So in continuation with this, speed of rotor MMF relative to the stator MMF, right? So this is basically the relative speed between the stator field and the rotor field, and what we know is the speed of rotor MMF is 1500 rpm. The speed of stator MMF is also 1500 rpm. So the difference between the two, or I must say the relative speed between the two, comes out to be 0, right? What it implies? So it is 0 rpm. The rotor's produced MMF or rotating magnetic field and the stator produced MMF or the rotating magnetic field, they both are rotating at a speed of 1500 rpm and in the same direction. So the relative speed between the two comes out to be 0. Now let us move to the last part of the question. Are the conditions right for the development of net unidirectional torque? The answer is yes. Why? Because we have got two rotating magnetic fields. Both are stationary with respect to each other. They'll interact for production of a steady torque on the rotor of the machine. So this completes the first part of the question. If there is any query, you may write in the chat box. Now, let us move to the second part of the question. It is also based upon the induction motor, three-phase induction motor only. Now, let us try to first understand what the question is. The resistance and standstill reactance per phase of a three-phase induction motor is 0.1 ohm and 0.4 ohm respectively. So, the resistance and standstill reactance per phase of a three-phase induction motor is given as 0.1 ohm and 0.4 ohm respectively. So it is basically the resistance and reactance of the rotor of the machine, right? So rotor resistance equals to 0.1 ohm per phase and rotor standstill reactance is given as 0.4 ohm per phase, right? Now, beyond this, if 100 volt per phase it is induced in the rotor circuit at the time of starting, right? So, at the time of starting means the standstill induced EMF in rotor circuit is given to us. So, besides these two, what else is given to us is standstill rotor induced EMF, and it is given as 100 volt, and this is the per phase value of the induced voltage, right? So, we are supposed to calculate the rotor current and rotor power factor under two conditions. The first condition is when the rotor is stationary, and the second condition is when rotor is running with a slip of 5%, right? So, when rotor is stationary, let us start with the first part of the question. So, when rotor is stationary. When rotor is stationary, we need to determine the rotor current and the rotor power factor, right? So, the rotor current, let me write here, rotor current can be written as rotor induced EMF per phase at standstill divided by rotor impedance at standstill, right? So, the rotor current when rotor is stationary can very well be determined as the ratio of rotor induced EMF at standstill to the rotor impedance at standstill, right? The rotor induced EMF at standstill condition is given to us as 100 volt. And what about the rotor impedance per phase? The rotor resistance per phase is given as 0.1 ohm, and the rotor reactance per phase at standstill, as we know that the reactance is dependent upon the operating slip of the machine. So, the impedance at standstill can very well be written as 0.1, that is rotor resistance. So, 0.1 square under root 0.1 square plus 0.4 square, right? Solving this, you will get the rotor current in amperes per phase, right? Solving this, you will get the rotor current equal to 242.5 ampere. So, it comes out to be 242.5 ampere per phase. So, this was about the rotor current at the time of standstill. Now, let us consider the rotor power factor under the standstill condition. So, the rotor, we know the rotor circuit resistance as well as reactance. The rotor power factor angle can very well be determined as theta equals to tan inverse x upon r. The x upon r at standstill is given to us as 0.4 and 0.1. So, x upon r ratio is 0.4 divided by 0.1. So, tan inverse 0.4 divided by 0.1 will give us the power factor angle of the rotor circuit, that is theta, and cosine of theta will give us the operating power factor of the rotor circuit at the standstill condition of the machine. Solving this equation, you will get the operating power factor to be equal to 0.2425, and of course it is lagging in nature. 0.2425 lagging, right? Now, let us now proceed to the second part of the question. The second part is actually asking for determination of the rotor current and the operating power factor of the rotor circuit when motor is running with a slip of 5%, right? So, let me first rub this portion to make some space. Now, when rotor is running with a slip of 5%, the induced EMF as well as the impedance of the rotor circuit will get affected. Why? Because it is dependent upon the operating slip of the machine. The rotor induced EMF under normal running condition with a slip of say S comes out to be S times the induced EMF at standstill condition. So, when rotor or motor is rotating with a slip of 5%, right? The rotor induced EMF will be the rotor induced EMF will be equal to what? 0.05 times 100. This much volts per phase, right? What about the rotor impedance? And rotor impedance will be equal to under root 0.1, that is rotor resistance square, plus S times X square. So S times, that is 0.05 multiplied by 0.4 square of the same, right? So knowing these two values, I can very well calculate the current, rotor current, when rotor is running or motor is running with a slip of 5%, with a slip of 5%, right? It would be equal to the induced EMF, that is 0.05 S times the standstill induced EMF, 0.05 multiplied by 100 divided by the impedance here, that is 0.1 square, plus 0.05 times 0.4 square, right? Solving this, you'll get a rotor current of 49 ampere, right? Likewise, we can determine the operating power factor under running condition. So the operating power factor under running condition is cosine of 10 inverse Sx upon R, where X was the standstill rotor circuit reactance. So cos theta under this running condition, here right hand side on the board, we are considering the running condition of the rotor. So cos theta would be equal to cosine of the angle theta, and theta is 10 inverse Sx upon R. So it can be written as cosine of 10 inverse 0.05 into 0.4 divided by 0.1, right? So solving this, you will get the operating power factor as 0.98, and of course it is lagging again. So what's the conclusion? You just pay attention over the value of current obtained here and the value of current obtained here. You can very well see that at standstill condition, the current drawn by the rotor circuit, current flowing in the rotor circuit, I must say, is quite high. Why so? Because when rotor is at standstill condition, if you see the equivalent circuit of the machine, you will find the conditions of short circuit actually prevails, right? So under these conditions, the current flowing in the rotor circuit is quite high, and the operating power factor of the rotor is quite low. It is 0.2425, right? While under normal running condition, when motor is operating with a slip of, say, for example, 5% as given in this particular question, the current gets reduced to 49 ampere and the operating power factor got improved to 0.98 lagging, right? Now, let us move to next question. Let us try to first understand what question is asking. The resistance and standstill reactance per phase of a 3-phase 4-pole 50 Hz induction motor is 0.2 ohm and 2 ohm respectively, right? So this is basically the rotor circuit resistance and the reactance under standstill condition. So the machine is a 3-phase machine. Number of poles for which the machine is wound is 4. The frequency of supply given to the machine is 50 Hz. The rotor circuit resistance R2, let it be, is given as 0.2 ohm per phase, and the standstill reactance, let it be X2, is given as 2 ohm per phase, right? The rotor is connected in star and induced EMF between slip rings at start is 80 volt. What does it mean? It is a slip ring induction motor, right? Between two slip rings, the induced voltage is given as 80 volt, right? The induced voltage is given as 80 volt. What it implies? It implies that this 80 volt is the line induced voltage in the rotor circuit, right? So the induced line voltage is given as 80 volt. If at full load motor is running at a speed of 1440 rpm, we need to calculate the first part of the question, the operating slip, right? Second part of the question, the rotor induced EMF per phase value. Third part of the question, the rotor current and power factor under running condition, and the rotor current and power factor at standstill when slip rings are short circuited. Okay. The induced EMF here is the line induced EMF at standstill condition. Okay. Let us start with the first part of the question. We need to determine the operating slip of the machine, the rotor induced EMF per phase under running condition, rotor current and the power factor, and the rotor current and power factor at standstill condition as well. Standstill condition is the condition when operating slip S of the machine is equal to 1. So first, let us solve the first part of the question. We know that operating slip is given as Ns minus Nr upon Ns. Ns is the synchronous speed of the machine, and where Ns equals to 120 F by P, and we can very well calculate it. 120 into frequency of 50 Hz divided by number of poles of 4, and the speed comes out to be 1500 rpm. The NR of the machine is given in the question as 1440 rpm. So the operating slip can very well be calculated as 1500 minus 1440 divided by 1500, right? Solving this, you will find that the operating slip of the machine comes out to be 4% or 0.04. So actually it comes out to be 0.04. When this is multiplied by 100, you will get the operating slip of 4%. So this gives you the answer of the first part of the question. The answer is very well given here. Now let us consider the rotor induced EMF per phase, right? So the induced rotor EMF per phase value would be equal to what? The given value is the line value. So I can write rotor induced EMF per phase would be equal to 80 divided by root 3. Solving this, you will get the answer of 46.2 volts. Agreed? Let us move to the third part of the question. The third part is asking for rotor current and power factor under running condition. So the operating slip of the machine is 0.04. Rotor current would be rotor current per phase value under running condition would be equal to what? The slip multiplied by induced rotor EMF per phase under running condition. under running condition, okay, divided by the impedance. Right? We have solved a similar kind of question on previous slide as well. So rotor induced EMF under running condition would be what? 0.04 multiplied by the per phase value of induced EMF, that was 46.2, divided by the impedance under running condition. So the impedance under running condition would be equal to 0.2 square plus 0.04 times 2. It is S times X square. Solving this, you will get a current of 8.58 ampere. 8.58 ampere. Agreed? So this is the current in the rotor circuit under running condition. Likewise, we can determine, I'm writing towards this side, we can determine the operating power factor cos theta as cosine of tan inverse x upon r under this condition. So I can write it as cosine of tan inverse x would be equal to 0.04 times 2 divided by the resistance of 0.2, and solving this, you will get the operating power factor to be 0.9285. Right? Now I need to determine the fourth part, the next part of the equation, the rotor current and power factor at standstill. Right? So similarly, it can be determined as at standstill, I can write rotor current as the induced EMF per phase at standstill, that is 80 divided by root 3 divided by the rotor circuit impedance at standstill. So 0.2 square plus 2 square. Solving this, you will get a current at standstill to be equal to 22.98 amperes per phase value, right? And the last part of the question is, we need to determine the operating power factor. So I'm writing in this space, the operating power factor would be cos theta equals to cosine of tan inverse x at standstill is 2 itself, and this is 0.2. So solving this, you will get the operating power factor as 0.0995. Right? So this is the answer of the fourth part of the question. Right? For any queries, you may comment in the chats. So that's all for this particular lecture. We'll come up with some more numericals in next lecture of the same subject on the same topic. Thank you.